All right, I'm going to go over the 2.1, 2.2 practice problems that were due on Monday. I already went over number 6 and number 8, so if you had problems with those were the two you asked me to go over in our review on Monday, and I believe I went over them yesterday. So if you need help with the 6 and 8, then go back to that video. Okay, I'm pretty sure it's the video from Monday and Tuesday. Okay, so number 1 says that Mahfoud and Muhammad Ali are pushing a super heavy box of books into the science classroom. The boys are pushing on the same side of the box and in the same direction. Mahfoud pushes with 140 newtons of force and Muhammad Ali pushes with 120 newtons of force. Draw a free body diagram for this scenario. Well, we are going to have our object being the box, and you could have drawn two forces on the... It doesn't say which way they're pushing it, so as long as these two forces are on the same side of the same side of the box pushing in the same direction, you're good to go. And these are applied forces. They are moving the box. It says it's moving, so since they're sliding it on the floor, there is a friction force here. We don't know what the value is exactly. If you wrote, so you could have also just combined, you could have combined these two into one arrow like this, and it would say 260 newtons. Combine them if you just add 120 plus 140. And this is the F applied. So either way you did it, I'm not going to mark you wrong if you did it this way or this way. It's right either way. But for the friction force, this has to be, because the box is moving, know that this has to be less than 260 newtons, right? It has to be less than 260 newtons. Okay? It can't even be equal to 260 newtons. It must be less than 260 newtons. We also have the normal force, which doesn't have a value here. I didn't give you one. And we have the force of gravity. So, and the same would be for this one on top. Either way you wrote it is good. All right, what is the net force on the box? We just figured that out right here. It would be 260. Or if you said we can't know for sure because we don't know the friction force, that would have also been a really clever, good answer. But if you said the net force on the box is 260, that would be fine too. Is this an unbalanced or balanced force? We know that it's unbalanced because it's moving, right? If it was balanced, it would not be moving. And then I asked you to please describe what happens to the velocity and the acceleration of the box. So because the force is constant here, we are going to have a constant velocity, meaning no acceleration. So, undo that. We would have constant velocity, means no change in velocity, meaning there's no acceleration, or acceleration equals 0. Okay? All right, then number 2. Number 2 says that two dogs are playing with a ball. They are pushing on the ball with their heads in opposite directions. Dog A pushes the ball with a force of 138 newtons in the rightward direction, and dog B is pushing the ball with a net force of 42 newtons in the leftward direction. Draw a free body diagram of this scenario. So if we do that, the ball, I'm going to draw it as a square. So we have one dog pushing in the rightward direction with a force of 138 newtons. And this, we can either call this force applied dog A. Something like that would be great. And then the dog B is pushing the ball with a force of 42 newtons, so smaller. So the arrow should be smaller. 42 newtons of applied force in the leftward direction, and that is B. Then we also have the normal force, of course, and the force of gravity. All right. Is this a net, or what is the net force on the box? Well, to find that, we're going to have to take 138 newtons and subtract 42 newtons, and that will give us 96 newtons of force rightward, or just to the right. Letter C says, is this a balanced or unbalanced force? Well, this is unbalanced, right? This is 96 newtons. I don't know why I wrote F here, sorry. Newton force is what I wrote. Newtons to the right, so this would be unbalanced. The ball is moving. Please describe what happens to the velocity and the acceleration of the ball. This is the exact same thing as the question before. As long as the dogs don't change the force that they're applying to the ball, then the velocity will remain constant, right? They will be at a constant, they'll be constantly moving to the right at a constant speed. So if velocity is constant, then that means acceleration is 0. We are not accelerating. The dogs aren't speeding up or slowing down. All right, number 3 says 11th and 12th graders, or 11th and 12th grader playing a tug of war with a long rope, with a knot in the middle. The 11th grade is pulling in one direction with a force of 248 newtons. So for A, we're going to have to draw a free body diagram, so we might as well do that now. So the 11th grade is going to be pulling to the right with 284 newtons. And the 12th grade, of the 12th grade, I switched this up. Of the 12th graders that are attending school that day, Hindu is pulling with 60 newtons of force. So we have Hindu with 60 newtons, and this should technically be much shorter than this one. And this would be, what kind of force? Well, we'll come back to that. Okay, so Hindu's pulling with 60. Muhammad Ali is pulling with 80, so a little bit more. And Lena is pulling with 56 newtons. Oh, there's 4 people here. Lena, 56. Yusra with 88 newtons. Okay. Oof. So it probably would have been easier if you combined all of those, right? So let's add all of those up. If we add all of those up, we get 284 newtons that the 12th grade is pulling with. And, of course, I told you just that the 11th grade is pulling with 284 in the opposite direction. All right, draw a free body diagram of this scenario. We have started to do this, but we have not labeled what types of forces we have here. So we're drawing a free body diagram of the knot in the middle. So this is a rope, right? So this would be tension force, and this would also be tension force. These are not applied. It's tension because we have a rope. And that is it. There's no normal force on this. You could write the force of gravity if you want, but yeah, you can write that. Why not? Force of gravity, because it would move down if you weren't pulling it super tight. But you didn't need to write the force of gravity. If you didn't draw the force of gravity, I'm not going to mark you wrong for it, because the most important ones are that you got the tension force here. And is this balanced or unbalanced? Well, they are both pulling in opposite directions with the same force. So this would be a balanced force, meaning that the knot isn't moving. Please describe what happens to the velocity and acceleration of the knot. Well, the velocity is 0. It's as long as they don't change their tension forces on either side of the knot, then the velocity will stay 0. If the velocity is 0, then acceleration is also 0. All right, number 4. I think we already did this, didn't we? Let me check. No, we'll just do it right now. Okay, so the gravitational strength of Mercury is 1/12 as strong as the gravitational strength on Earth, and a boy has a mass of 65.45 kilograms. What is the boy's weight on Earth? All right, so write all of our knowns, unknowns, and equations here. We have that the gravitational strength on Mercury is 1/12 as strong as the gravitational strength on Earth. We plug this in, 9.8 newtons per kilogram, and we find that the gravitational strength on Mercury is 0.82 newtons per kilogram. So we know gravitational strength. We know that the boy's mass is 65.45 kilograms. And we are looking for the boy's weight, Fg, on Earth. All right, so we will use our equation, Fg equals mass times gravitational strength. We don't have to arrange anything here. We can just solve, and we get Fg equals his mass, which is 65.45 kilograms, times, we're on Earth, so we'll do 9.8 newtons per kilogram. Kilograms cancel, and we get that his weight on Earth is, and we have 4 significant figures here, is 641.4 newtons. Part B wants us to find what is the boy's weight on Mercury. So we can just erase this. Well, let's keep our, we'll write 641.4 newtons Fg on Earth over here, and then we'll erase this stuff. Okay, we're not looking for Fg on Earth, we're looking for Fg on Mercury. All right, we already figured out our gravitational strength on Mercury, so we actually just have to plug everything in again. 65.45 kilograms times our gravitational strength on Mercury, which is 0.82 newtons per kilogram. And when I plug this into the calculator, I get that the boy's weight on Mercury is 53.67 newtons. All right, part C wants you to compare the normal force acting on the boy on Earth and on Mercury. How do they differ? Well, the normal force, remember the boy is standing on Earth. He has the force of gravity on Earth, and so his weight, Fg on Earth, is 641.4 newtons. His normal force, because he's not moving through the Earth, is the same. It's 641.4 newtons on Earth. And then on Mercury, it would be his force of gravity, or his weight, would be 53.67 newtons. Therefore, his normal force would be the same, 53.67 newtons. All right, if we look at this in a calculator, remember that the gravitational strength here is 1/12. The gravitational strength on Mercury is 1/12 the strength on Earth. So we actually see that the boy's weight on Earth is 1/12, the boy's weight on Mercury, here, this one, is 1/12 what it is on Earth. And so the same can be said for the normal force. Gravity is, or the boy's weight is 12 times more on Earth. Therefore, the normal force is also 12 times more on Earth than it is on Mercury. If you said something along those lines, that would have been killer, stellar, excellent. All right, number 5. A mobile, however you want to say it, hangs from 3 strings from the ceiling. The mobile has a mass of 432.0 grams, and it is at rest at the end of a string. The end of the string, the 3 strings. No motion is occurring. What is the weight of the mobile? And the hint is to be sure you're converting everything to the proper units before calculating. Okay, so we just want to know the weight first. So let's write all of our usual things. We know that the mass of the mobile is 400, mass equals 432.0 grams. So how many kilograms is that? We know that 32.0 grams. We know that 1,000 grams is 1 kilogram. Cancel out grams and grams. And we find that the mass is 0.4320 kilograms. Okay, so all of this stuff about the three strings, we're not going to need any of that information until we get to the free body diagram and the questions about tension. So we don't need to, the fact that the mobile is hanging from strings doesn't make its weight any different on Earth. So what we're looking for is just its weight. We are on Earth, or because I don't indicate otherwise, so it's 9.8 newtons per kilogram. Our equation is Fg equals mg. We don't even have to rearrange, we just have to solve here. So the weight of the mobile is the mobile's mass, which is 0.4320 kilograms, times the gravitational strength on Earth, newtons per kilogram. Plug that in, and we get that the mobile's weight on Earth is and we have four significant figures, so we have 4.234 newtons. So that is the answer for part A. Part B says, how many newtons of tension force are being applied to the mobile? All right, so let's look at a diagram here. Okay, so this is what the mobile would look like. Let me explain. This is the circle, the piece that I think you've probably seen a mobile before, right? It's a little thing that spins above babies' cribs. So it's just this, like, you could even think of it as like I don't know, how do you describe a mobile? It's like this. You got a hoop, and then you got little toys dangling down, and the baby lays underneath and is all happy and smiley and looking up at it. See, there's the baby, okay? So this thing spins around, and it's attached to these three strings in red here, okay? So we have three strings in red. We just figured out in part A, erase the baby there. We just figured out in part A that the force, or the weight of the mobile is, and I just erased it, what was it? So Fg equals 4.234 newtons, okay? So if this is 4.234 newtons, let's draw a free body diagram here. We have force of gravity, which is weight, of 4.234 newtons. These three strings on top, because the mobile is not moving, they're all tension force, right? Because they're strings. They must equal this force of gravity, this weight, because the mobile is not moving down, right, or up. It's not super strong, and it's not the strings aren't pulling the mobile up, and the weight isn't pulling the mobile down to the ground. So the tension force, we want to know how many newtons of tension force are being applied to the mobile. So actually, we don't even have to divide them amongst, like, I'm not even asking you the individual tension forces in each string. I just want to know how much total tension force is there. Well, it has to be equal to the force of gravity, or the weight that we just found. So the answer would be 4.234 newtons of tension force for part B. What type of that's the wrong one. Whoops, I wrote this wrong. What type of net force is acting on the ball? I meant the mobile, sorry. Well, none of you asked me about it, so I think you're probably just used to my pregnancy typos now. So anyway, what type of net force is acting on the mobile? Well, there's no other forces acting. I actually just drew the free body diagram right here. This is the free body diagram. Or if you just wanted to draw this as one arrow, like if you wanted to draw Fg of 4.234 newtons, and then draw your tension force the same, that would have been correct. Either this one or this one is good. So, what is the net force acting on the mobile? The net force acting on the mobile is 0. These balance each other out. It's not moving, so it's a 0 net force, meaning it's a balanced net force. Draw a free body diagram of the mobile and all the forces acting on it. Either one of these, like I said, is the correct answer for that one. All right, if I had asked you, which is probably what I will do on the quiz, if I had asked you some questions similar to this, or like the same exact scenario, but I asked you what was the individual tension force in each of the strings. There are 3 strings, right? 1, 2, 3 strings. They all together combined have a tension force of 4.234 newtons. So how could I find the individual tension force of each of the 3 strings there? What I could do is divide 4.234 newtons, divide that by 3 strings, and then I'll find how many newtons of force are in each string. And if I did that, I would find that there is 1.411 newtons of force in that string, and in that string, right? So that's also just another way of, just so you know, it might not be as simple as this one was. It's going to be a little more, that question would be what's the tension force in each of the 3 strings, not just what's all the tension force together. All right, let's do the last one, number 7. It says, Mark pushes a box as hard as he can, but the box is too heavy and does not move. What type of friction is occurring between the box and the ground? Well, the net force on the box, F net on the box, equals 0 because there's no movement. This is balanced. When we have a balanced net force, and obviously this is I tell you actually that what type of friction is occurring. Remember that when we have a 0 net force, the type of friction that is occurring is static friction. That is when, static with 2 C's, cool. That is when Mark is pushing with, let's say he's pushing with exactly X newtons. The static friction force is exactly X newtons as well. It's exactly the same. It's not, or it could be more. It's greater than or equal to X newtons actually. So if he's pushing with 120 newtons, I'm drawing my arrows the wrong way, sorry. Let's try that again. I do that every time when I talk about pushing. Okay. So he's pushing to the right. Mark is pushing to the right with 120 newtons. The static friction, this is the friction or the force applied. This is my friction force, is greater than or equal to 120 newtons, right? So if he's pushing with an applied force of 120, the friction force, that is static friction in fact, must be equal to or greater than 120 newtons to prevent that box from moving, to keep that at a balanced net force, okay? All right. And actually, yeah, okay. So is the net force balanced or unbalanced? We just said it's balanced. So actually that means, sorry, I made another mistake. Gee whiz. Sorry, it's early. This is actually exactly 120 newtons. So what was my mistake here? Why is that a mistake, when I said greater than or equal to? It has to be equal to 120 newtons. What would happen if that static friction force was greater than? Let's say that it was 140. What would the net force on the box be? It would be 120 newton, or 20 newtons this way. Is the static friction force going to push the box? No. Right? So it has to be exactly equal to, we can't actually have greater than 120. It's exactly equal to 0 newtons, because we have to, when we draw our net force diagram, it would be 0 newtons. It has to have a balanced force so that it's not, or balanced net force so that we know for sure it's not moving. If this was 120 or 140 newtons, it would not be a net force of 0, it would be a net force of 20 newtons to the left. So I apologize, my bad. Okay, so the type of friction is static. It is a balanced force. Explain your answer for part A with words and a free body diagram. Well, I just did that. So I just explained that with words, so I'm not going to explain the exact same thing again. And I already did number 8. So that is it for these questions. Someone asked if this is how the quiz will be. Yes, these questions will be similar to the questions that are on the quiz tomorrow. If you have any questions concerning what I went over today, please let me know. I'm not going to answer questions after 5 p.m. your time, so be sure you ask them before then. All right, have a good night. Bye. Or a good day. Sorry.